The next thing we want to start talking about is after you go out there and create these basic skins of buildings, and how we start infilling in with all the different systems that are ultimately part of what's necessary to make the building operational and functional. And there's really a whole series of different systems. And before getting into the modeling, I wanted to actually think a little about all the different types of systems and really what drives the design of those different systems. Or controls how we think about coordinating the people who are designing those different systems. So the building, again, it's kind of like a living organism. There's different things that support it. The skin's there, kind of like is on a human body. But underneath the skin, one system that almost everyone will start to understand is the structural system. So all the columns and the beam systems, everything that's all about supporting it structurally needs to be in there to actually indicate how that's going to work. So it's one of the systems we tend to design and coordinate. But there are a lot of other different systems that are in here too. For example, there's a whole series of different mechanical systems, different systems that are all under, we call them MEP systems, that support different sorts of functions. When people talk about mechanical systems, what they tend to be actually talking about is heating, ventilating, and air conditioning systems. So HVAC is another way of saying that. So it's air handling, moving air around through the space, making sure that we're heated, that we're cool, that it's ventilated properly. And those are some of the big considerations, really, of just making sure that the space is safe and habitable. It's not only that it's kind of hot enough and cool enough, but actually there's enough fresh air moving through it that it doesn't get stale, that any of the fumes that are here that we need to be evacuated have to have taken away. If there's any like harmful fumes in an environment where we have some output that's producing something that would be noxious to us, or just, you're in a room that just feels still or kind of dead. Grandma's house was always this way. It was kind of a little bit just, the air didn't move enough in there because she needed to open the windows more often. That's what we're trying to fight. We're trying to fight the issue that like rooms need enough ventilation to kind of keep them fresh. Sorry, Grandma. If you're listening, nothing personal. Okay, under mechanical systems and HVAC, there's a couple other ones that are really kind of critical within there too. We have a whole host of different plumbing systems. And under plumbing systems, there's actually a bunch of different ones. If you think about all the pipes that are running around in the building, all the things they're trying to do. We have the whole idea of, we have water supply systems. So those are the pipes that bring water to the places we need them. They bring the water, the hot and cold water to the sink. Typically just the cold water to a toilet. Just cold water to a water fountain. Systems like that. Okay. There's also another set of pipes that tends to run around called the sanitary system. That's all about bringing water away from the fixtures. So all the wastewater and making sure that it's actually channeled either to be recycled or reprocessed or disposed of going out to the sewer system. There's a whole sanitary system. There's also the whole notion of a sprinkler system. So each of these different systems have different characteristics. Actually, in this room, you can sort of see the sprinklers. There they are, 1, 2, 3 in the back of the room. There's one over there. Is one on this side? Oh, it's back over by the sprinkler. It's not a great place with the effect behind the speaker. There's going to one back over here behind the speaker too. You probably wouldn't want them to be behind the speakers because if there was a fire, the speaker would be blocking the ability for it to throw water. Each of these different systems is designed using all sorts of different considerations. As we've gotten greener and greener in our buildings, this has actually even gotten a little more complex because this building's an example of one where, we actually use gray water in sort of an interesting way. So what's happening is out of the sanitary system, there's two different things going on. There's gray water coming out, and there's what's called black water. Which is ultimately destined towards typically a sewer or some sort of processing plant. Black water is, it's the water from the toilets, it's carrying human waste, it's carrying things that can't easily be recycled. Okay, so that gets funneled off in different ways. Gray water is actually water that can be reused. So when you're washing your hands in the sink and that water may have a little soap in it, it's probably going to show up later flushing one of the toilets. Okay, it's captured. We don't just send that right down the sewer system. We actually capture that and recycle the water. So what happens is gray water sort of comes back into the system as part of the water supply. Not the water supply for everything. Someone asked us this morning. When you're in the restroom and you see that, oh, this building uses recycled water by one of the toilets or the urinals, okay, the gray water is being used to flush the toilets, okay? It's not being used to feed the water fountain, and it's not being used to wash your hands, okay? It's being used to sort of supply water to some of the fixtures, and just as a system designer, this adds a layer of complexity to it all, because now you have to start worrying about different types of systems and what type of water. Is it feeding fresh water? Can it feed recycled water? Oh, other things we try to do, we try to catch water on the roof and then actually funnel that down to cisterns where it's collected in the courtyard and reuse that wherever we can for irrigation and try and flush toilets and things like that with it, because there's different types of water. There's potable water, which we're concerned about the sanitariness of it. For the toilets, we're not concerned that it has to be 100% clean. So, someone asked this morning, so why do they put that little thing that says recycled water, in the bathrooms? It really is literally to keep you from drinking the toilet water. And it seems really, really silly that you have to do things like that. But, the legal system says that you have to warn people about stuff like that. So if anyone happened to be drinking the toilet water, I can't even say that without cracking up. If you happen to be drinking the toilet water and you got sick because of that, you're not going to be surprised. Yeah, I can't even say that with a straight face. Okay. Beyond that, we have systems like electrical systems. And electrical systems, there's a bunch of them. There's all the power systems, the things that actually supply the plug loads and all the power for your computers and the printers, stuff like that, and the lighting, kind of sort of high power systems. There's all sorts of low voltage systems in here. Control systems that control alarms and door locks and sensors and, networking systems. And there's just really an incredible amount of wire that runs through the building. It's not all about supplying power. So sensors and controls and networks. So if you really expose the building and looked at, it's kind of like looking at the human body. You have all these incredible systems. I have these systems for bringing in air and then oxygenating my blood. I have this whole circulatory system that gets the blood that my heart's able to go ahead and translate to, or the oxygen that my heart's able to translate into something that can be fed through my veins to kind of keep all my outer limbs happy. It's really an incredibly complex system of organisms. Even, on the electrical side, this whole notion that really, as I'm deciding either what I'm doing or moving my hands, the decisions are actually happening up in here. There's this incredible system of wiring to the nerves that actually makes my mouth move or makes my fingers move. We're really incredible organisms, and buildings are too, in terms of how things are being designed these days. So as you think about these different systems, and as you're trying to fill in all these different systems, it sort of comes up really quickly with the notion of, okay, great. We have all sorts of stuff we want to have happen in a building. We have all these different systems we want to sort of get into a building. How do we make that happen? And how do we coordinate that work? So to understand that, I'm actually going to open up another model. Going to open up a project. It's out there on the coursework server if you want to open it up and follow along. I happen to have it just here on my own machine in the system or session 15 folder. But it's a basic little building which was set up, really to illustrate this concept. It's not a very complicated little building. It's kind of like the type that we have, here in Palo Alto or down in San Jose. We have some space on the bottom, which is designed to be more of a retail space, and space above that's designed to be more of an office space. Not really finished out very much, but it's kind of a very common model of the way we do buildings around here. And you can look at, the plans and sort of see a little bit how the space is organized. Within this design, there's a lot of open office space. There's kind of a shared conference room, kind of a core to the building right in the center. Where in that core area, we have some bathrooms, men's and women's bathrooms, a stairway, some elevators, a little storeroom for mechanical equipment, and a little atrium that runs all the way up and down between the top and the bottom of the building to bring some light in there. So I can take a look at that in 3D also, or do a nice 3D section. Let me zoom on out, or expand the section box on out so you get a better sense of the building. Okay, but this is kind of a very common point where we get to in our architectural design, where we've designed a number of aspects of the building. We pretty much understand it architecturally, and even as architects, we've allowed a certain amount of space for running utilities, for running a lot of the building systems. In this lower space down here, with the retail space, you'll see there's no ceiling. So in those spaces, very often the ductwork, the piping, a lot of times that stuff's exposed. Some people like that look. They may put a ceiling in there depending on how they want to finish that architecturally. Up here in the office spaces, we've actually included a ceiling space and a little bit of space between the ceiling and the floor above. And it's really not a very big space. In this building, I think there's probably only about 2 or 3 feet in there. It's really a very, very tight space. And somehow, in that 2 or 3 feet, you've got to get a structural system, room for mechanical ductwork, get your piping in there, and get your electrical running through there, all in that very tight space. So if you think about the types of construction problems we have, the types of problems we have as designers, that issue of how you take that really small space and get all these different things to happen in that really small space in a very coordinated way, considering that each of these different systems is probably being designed by a different designer from a different company who don't really have a contractual relationship with each other. Okay, it's amazing that it actually works. And that's really probably the biggest challenge we have, and that where building modeling can actually come in most useful. It's really coordinating these different systems and getting the work of the different designers together. Because it used to be we designed these 4 different systems independently, maybe even more than 4 systems there. We'd all come up with our independent drawings, and typically where you finally figured out you had a problem was out in the field, and you tried to put it all together and realized things didn't fit. It was a little late. It was a very expensive problem to fix that part. Maybe you could try to figure it out from the drawings, but it was very hard. With the building models, I can actually get all these different types of information together into a single place, and hopefully that'll make it a lot easier for us to coordinate and find the problems before we actually get into the field. Okay? And that's really the point about BIM supported construction coordination. So, as you think about these different systems, let's try this. Okay, if I've got 4 or more systems that have to be designed here, and I take 5 or 6 different designers and turn them loose and say, great, you got 2 feet, go ahead and design your system, optimizing for what you need. Okay, let's see how it all turns out in the end in terms of coordinating everything. What do you think the likelihood of actually coming to some sort of good outcome is going to be? Okay, it doesn't make sense to sort of just turn everyone loose at the same time and say, we'll work it out in the end. In fact, there really is an order to these things, and that order, it's not sort of based by, who's the biggest bully or who has the biggest contract or something like that. There actually is sort of a logical order to this in terms of how this typically happens. And really, so much of what it's all about is the notion of really downstream impact. So you think about each of these different systems, and if one of these types of designers makes a decision, how impactful is it on the people downstream who are going to be following them later on in the process? And the things that are sort of the most impactful, you tend to like to get those decisions made first. Okay, and things that are sort of, the other thing that I'll describe it as is there's this whole notion of flexibility, which is the other big consideration. Things that are flexible and don't really impact a lot of other users can get pushed last. Things which are relatively impactful and don't have a lot of flexibility tend to get done first. Okay, as you approach this and trying to figure out who gets to sort of figure out how their system gets laid out first. So in this scheme of all these different systems, who do you think actually has the most impactful thing to go through and decide, who has the least flexibility to go through and change it? Yeah, it's almost always, structure has to happen relatively quickly. The structure, in fact, structure should probably be happening at the same time the architectural design is going on, because if you can't have a big open space like this and we need to put some columns in there and beams in there, we should know about that pretty early. So we can sort of factor that into the architectural scheme. So structural almost always goes first. Okay. Once you have the structure in there, and so in that little 2-foot space, the structural engineer is putting in some beams, whatever they're putting in there to go through and support the structure. Who do you think comes next? Yeah, mechanical is almost always second. It turns out mechanical systems are actually relatively complex to go through a design. In order to really get them efficiently designed so they're operating well, there's this whole notion of, ducts and the size of ducts and the lengths, and it's actually pretty finely tuned to make sure that just the right amount of air gets to each of the different endpoint locations and we're moving that air well. Mechanical systems are actually, they're relatively inflexible. Like, you don't like to have a duct that goes down and up and over. Every time you add one of those bends, it actually greatly decreases the efficiency of the system. So we tend to like to think about ducts as being relatively simple runs where things are relatively straight. So for example, we often sort of try to run the ducts under the structure. Or we'll think about if the structure has open webs, has some ability to run the ducts through the structure, okay, we can run it through here. But they tend to exist as a whole layer to themselves, and they tend to go second just because they're pretty impactful in terms of trying to decide, the ultimate order of things. Now of the plumbing systems, let's talk about them next. I'll give you that one. It's definitely within plumbing, or number 3, so it tends to go. Of these different systems, water supply, sanitary, and sprinkler systems, which one of those do you think is sort of the most constrained versus flexible? Okay, given the physics of the situation, which of those is the hardest system to design?
Sanitary?
Yeah, it's the sanitary system. And the reason the sanitary systems are so hard to design is they tend not to have a lot of back pressure. We don't put a lot of pumps into them. We try to use gravity to go through and basically let everything flow downhill. Okay, so sanitary systems, the pipes all have to run downhill at a very specific slope. If they're flat or if they go uphill, we have very big problems. Okay, so everything has to run downhill. So they're actually probably the hardest of the plumbing systems to define. Water supply and sprinklers, you could argue about which one's greater there. Sprinklers, they're all designed, there's back pressure on them. So sprinkler pipes can go up, down, and around, as long as we get the amount of pressure we need in each of the different heads. Okay, they're okay. They tend to be fairly regulated about the locations of where the sprinkler heads have to be and how much pressure is coming at each of the different heads. But piping that has pressure behind it is pretty good. You can run it up and down. If I needed to go ahead and run a pipe up, over, and around, that's okay. I can do that. There's some loss, but it's really not as big a loss as it is to the air system. So water supply, sprinkler systems, they usually kind of check in at number 4. Finally, my lowly electricians. Actually, that's probably the way to really go. The people who run the high voltage lines probably have more control than the people who run the sensor networks. But really the nice thing about electrical is whether it's running through conduit or running through just wires that are in Romex or some other sorts of system, wiring is very, very flexible. You can run it pretty much anywhere. It doesn't really impact the performance very much. Unless you have a very high voltage line where you're worried about some sort of voltage loss through the length. It's incredibly flexible how people run electrical work. So there is sort of a hierarchy. It sort of plays out in design. It also tends to play out in the field. If there's a problem in the field, there's a hierarchy to who usually gets asked to move their stuff. And usually the plumbing and the electrician, they have to move things before the structural or the mechanical people have to move things. But trying to get all this work coordinated or even prefabricated before it gets out to the job site is really where the game is right now. A lot of Martin's research is all about how you can prefabricate sections of buildings and really just assemble sections of buildings as opposed to trying to have this go on out in the field where the coordination burden is much greater there. So just lots of room for kind of making very powerful and impactful changes in this. But what does that mean for us for building designers? We're going to go through and learn how to model each of these different systems. That's really what we're going to be doing for the next assignment, not for assignment 4, which you're about to get but for assignment 5 of modeling all the structural systems, the mechanical systems, the plumbing systems, and the electrical systems, and ultimately trying to figure out how to use the building model to coordinate all those different designs, looking for any sort of potential problems and hopefully solving them. So to do that, let's go ahead and just kind of go through some of the structural stuff today. We talked a little about structural in the past, so hopefully that won't be too impactful. I'm going to wait and actually do the mechanical for next time because that'll keep you and the morning class kind of very much in sync with each other. Okay, what tends to happen is I often get ahead of myself in this class. So, we'll actually go ahead and get us back in sync with each other. And to think about structural, just kind of expose you to some of the kind of nuance in there. We can go ahead and if you want to, there's actually a couple models that you could take a look at on the coursework server. There is the finished structural model or a finished structural model for this building as well as one that only has the grids only. So let me just open up the structural model. Give you a sense of what the finished structural model might look like. Just so you know, this is actually a structural model that was created by a student in the class, 2 years ago? Something like that. And it's pretty typical of what we want to do here. We want to put the basic columns and beams in there, put some floor systems in here with some intermediate beams. We even went ahead and put in some bracing for some lateral support and some foundations. So this is all modeled in steel. We could just as easily model that in concrete, and I think we'll go ahead and do a concrete model today. But you can start with something like that. This is all based on a structural grid system. So if I go to one of the floor plans, you'll actually see there is a grid system underneath the building. And what I'll do is let me just kind of open up the grids, and we'll use that as a basis for just getting going. I'll say open a project, one that just has grids to it, and we can start there. Now, there's this whole issue about how you lay out grids, and I'm certain the structures professors could tell you quite a bit about the philosophy for where it makes sense to go through and lay out the grids. For what we're doing here, what do I want to say? There's kind of an art to it in terms of really trying to figure out the best structural grid locations. Part of it comes with experience. There's no sort of easy answer to how you necessarily go through and do that. But it's definitely related on the architectural features. What I'm going to do is I'm looking at the grids here. I'm going to link in the architectural model so I can see the architecture and the grids together, and you can get a sense of just how they work. I'm going to link a Revit model, and we'll do this next time together. We're going to link an architectural model to the structural model. Sort of see the two together. And you'll see the grids are actually sort of located based on different, what I hope will be good column locations and some of the core walls, some little knockouts that we put in the architectural drawing there. Then go up to the second floor. Hopefully we're going to be relatively good locations. After a while, you start thinking about just the best way to put the grids. Often grids aren't right at the outside line. Often the structure is just a little bit inside from the outer skin of the building. And that's the idea here. We're actually going to go ahead and kind of hold everything back just a little bit. We're going to have some columns at different locations that are a little bit less impactful. Put some of these kind of common walls in here. But it all starts with this notion of really just, can we go ahead and come up with good grid locations? Because you're just looking for locations where it'll make sense to break up the structure into some pseudo-regular grid that'll actually support everything without having the spans get to be too great. Because the bigger the spans are, the more these beams are going to take up room within this space, and it's going to get harder and harder for the non-structural people to work together. So that's one of those trade-offs. The grid locations and the spans will actually end up determining a lot about the heights of the beams, which will then make other people's lives harder to work with. Okay, so we'll start with just this notion of the grids. Within that, I'm actually even going to go through and just turn off the architectural model. So we're not looking at that. Go back to level 1. So, as we're thinking about doing this structure, we can actually do this pretty quickly in terms of once we have the grid location set up, there's all these tools that help us really lay out a structure on the grids very, very quickly, which are nice to work with. So, if I go to the Structure tab, and I start with the whole notion of just going with the columns first, Over here under the menu, the property, the type selector in the properties palette, you can see there's different sort of types of columns available. There's all these big wide flange sections. There's some concrete sections there. Again, if you want to load in some different sections, you can. Out in structural columns, you'll find different shapes. For example, there's a nice round column. I may load that one in. There's also some columns with drop capitals. If you have kind of a flat slab and you want to put a little shear reinforcement to keep the column from punching through, you can have a drop capital there. It's going to load in a couple of those. They'll just show up under the menu. So now in the type selector, there's some different types in here. Okay. What I typically do is, given that I have grids, I'll think about how to place things relative to the grids. Oh, with the columns tool selected, we have always this notion of, are you a structural engineer and architect? How do you think about the first level? Are you thinking about columns going up or columns going down from that level? I tend to think more about them going up, so I'm going to switch it to that way. Height going up to level 2. If you're a structural engineer, go to level 2 and tell them to go down instead. Either way, whatever sort of makes you happy. So we'll choose to put some columns in here from level 1 to level 2. That's the important part. We can choose the type of columns, and I'm just going to go for those little round columns for right now. One of the tools that's so useful is this notion of putting them at column grids. So if I choose the at column grids tool, I can just choose these grids. I'm going to choose those grids. When I'm done selecting all those grids, hard to tell, but it's actually suggesting a column at each of those different grid intersections. I'll say finish. And you have an incredible field of columns. Okay, pop that out. I'm going to turn that section box off just so it's not bothering us. An extra column hanging around there. Okay, so really quickly I've generated 32 columns there. If I want to go through and put beams in between those columns, it's going to be similar as a starting point. Yeah, just really basically before I start customizing the building very much, if I want to put a bunch of beams in and I want to put them in at level 2, I should go to level 2 and put them there because they're sort of below me from level 2. Okay, if I'm going to try and put them on level 1, I have to look and put them in the ceiling plan so I could see them. I'm going to go to level 2 framing. I'm zooming out a little bit. We'll go through and choose the beam tool. So the beam tool again has all these different types. We have some concrete shapes. We have some steel shapes that we can work with. I'm just going to go for a concrete shape for right now, 12 by 24. So let's go through and put this at the grids. And I'll choose those different grids. As I'm putting, oops, I have to control click there too. Okay, actually I should have paid attention to make sure they were going at the right level. I'll tell you in a second whether or not they did. Take a look at that in 3D. Yep, they actually did. What I should have done is actually just make sure when I'm putting the beams in, you can control what level they're on, whether on level 1 or level 2. Since I was on level 2, it assumed the work plane was at level 2, so it kind of followed through okay. So far so good. As I'm going through and putting these things in there, concrete and steel, they're amazingly similar to go through and model. But the only difference you have to worry about is this. With concrete structures, you actually get this very nice feature. The slab is here. You have some sort of beam that could intersect with it. And the nice thing about concrete, kind of like it does in real life, like it magically merges together and doesn't create much of an impact. So the beam depth and the concrete slab depth can actually work together. Okay, and so when you're modeling concrete, it's really, really easy. You don't have to worry about interference. When you're working with steel, though, you have to be a little bit more cautious. With steel, you often have like some deck and there's some sort of metal deck underneath it. So it's concrete with a metal deck underneath. When you go through and put the steel beams in, you don't actually want to have them protruding up into the column or into the slab. You want them sitting underneath the slab. Okay, so what happens in that case, if you're putting steel beams in, is you just have to remember to offset them a little, give them a little bit of an offset down. So how that looks is, for example, here's a beam, there's a Z offset. I just have to give it a little bit of offset, whatever it takes to lower it down so that it'll be beneath the slab. Okay. But again, since it's concrete, I'm not going to worry about that now. But that's really one of the few differences between thinking about modeling steel and modeling concrete. It's just allowing that steel doesn't have the ability to magically merge. You need to go through and be very explicit about its locations. Okay, just a few final things to get you going. Now, these big old bays that we've set up right here are currently about 30 by 30. And, well, you know, if I reinforce the slab appropriately, I might be able to go ahead and have a 30 by 30 bay. But I might want to put some intermediate beams in there to help support that, where these bigger beams are girders. And then I'll have smaller beams, which I'll call joists, that sort of run between, or just beams that run between them. So there's a really nice notion of something called a beam system, where a beam system is all about, if I take some sort of boundary and I fill it in with sub-beams, giving them a very regular spacing, you know, can I really dictate that all at once? And that actually works out pretty well. If I choose, again under structure, pop back out of here. You got things hanging off the end here that you can't even see. Okay, beam system. You have the notion of what level it'll be on. In this case, I actually want it to be on level 2. So I'm going to change it, the work plane, from being level 1 to level 2. Make sure they get up high. Next, I have the issue of really what the boundary is going to be, and I'm going to choose beams. I'm going to choose this. That boundary is going to get filled in by some sub-beams. Currently, there's a parallel line over here. That's indicating that it's going to put beams running parallel to this location. That may be okay. I can change the beam direction, make them run the other direction if I want to. Then you finally have, what do you want to have between those? And I could put in any of the structural elements. For example, I could put a lot more 12 by 24 beams in there. You finish that off. If that doesn't look so good, if you'd actually like those beams to be a little bit smaller that are running between, no worries. All we have to do is actually define another size. So let me choose the beam system, or I really don't have to do it in the system. Actually, let me just do it in terms of beams. I can say of the beam types, I have 12 by 24. If I want to duplicate that and make a smaller size, let me make sort of a 9 by 12, which will be 9 inches wide and 12 inches tall. I have a new beam size. Concrete's that easy in terms of specifying things. I can choose that whole system. If I tab a couple times, you'll get the whole system. There's the whole system. I can change it so that it's going to use those 9 by 12s instead. Okay, and the nice thing is, those will, if we change the grids, if we change all sorts of different things, those will size, resize, everything will kind of look pretty good relative to those dimensions. Now, as you keep going, you couldn't specify all these different bays one at a time, but someone asked this morning, quite rightfully, and it's a good question, can you copy and paste those around? And of course you can. Okay. Or I could go ahead and copy them over from bay to bay, kind of filling it in that way. So we can go through and set up something like that. Or where we'll finish tonight, there's this whole notion, okay, I can put a nice floor slab on this. See what I got in here. I got this lightweight concrete deck. There's this nice 6-inch concrete slab. I'll go ahead and choose this beam and that beam as the boundaries. This is one of those ones I actually want to put a floor slab over the entire space. Well, actually, I much. Like that, you could actually put floor slabs as subsections or across the entire space. It really depends on how you want to think about it structurally, whether it's one giant slab or you want to break the slab into smaller pieces that'll be analyzed separately structurally. I'll put it over the whole space right now. But what you're going to see I'm going to do is, as opposed to sort of choosing all the beams, whenever I have a big rectangle like this to do, what I almost always do is I'll choose 4 boundaries. And then I'll just use the trim tool to go through and join them all together. And why do I do that? It's just stronger to go through and define it with 4 lines than it is to define it with 32 different little lines. Okay, so that'll put a floor across the whole thing. If I drew a section right now, you'd actually see that's going to look amazingly good. Let's take a look at a section, see if that's true. Notice that in the section, it's already been a little bit smart in that it went through and it joined the beams and the floor slab together. So it's kind of smart enough to figure that out. So it's pretty nice in terms of what it needs to do. Now, to finish this all off, I have that single floor. It's looking pretty good. Of course, I should finish the whole floor before I do this, but we'll do it with a single floor. If I want to copy that up to the other levels, what I can do is just, again, grab this thing. And you know I love this trick. I'm going to go through and, grab most everything. Let me tell you about 2 different things going on here. There's analytical beams and columns and floors, and there's structural beams, columns, and framing, as well as floors. The analytical beams are the orange lines. They're the single line representations that indicate where the structural analysis would happen, not the physical representation of the beams. So when I'm copying, I'm actually just going to go through and copy the structural ones. It'll carry along its own analytical ones. So I'm just going to grab those guys. Copy that to the clipboard. And I'll say paste it from the clipboard to selected levels. Now I eventually learned this. Since those things are, as structural engineers like to think about it, actually attached to level 2, not to level 1. Okay, what I'm going to do is copy from level 2 to the 3rd level and the roof level. Okay, so I'm going to copy to level 3 and roof. And hopefully, we will have something that looks very much like a building. Now, no building would be complete without some foundation systems under there. Not to worry, we can grab some isolated foundations. I'll just put them at the columns, and I can choose there. Finish that off. Okay, and there you have it. In the last 20 minutes, we've actually put a structure, a couple holes in it in terms of what's going on. We were structuring our building. That's part of what we're going to be doing for the next assignment. So not 4, but for 5. We're going to do the structural system. One member of your team, you're going to work in a team on this, is going to go through and put a structural system inside the building. When we come back together on Thursday, we're going to talk more about mechanical systems and plumbing systems and how we model those things. Because someone else on your team is going to model a mechanical system and someone's going to model a plumbing system. And we're going to get them all together in the same building and make sure that they're coordinated and not creating too many hassles for each other. Okay, so that's where we're going with all this. It all starts with just the notion of let's build out the structure. I did that one first, and we'll keep on going with how we layer in the other systems and really make sure all that work fits ever so tightly into that incredibly small space, which is why you're eventually going to tell me, couldn't we make that space just a little bit taller? It would be so much easier with just even 1 more foot of space. We can talk about that as an issue, because that's really one of the things that architects have to consider is really, there's a trade-off between trying to squeeze all that in versus just making the floor height bigger. Okay, so let us adjourn for tonight. We'll stick around and answer some questions, but go ahead and have yourself a nice rest of the evening.